So if I were to roughly divide our course into 3 equal parts, the first part would be basically about lists, and that would just be simply, I would title it, memory locations, because that's the big challenge, which is that you got to learn how to deal with memory locations and references. The second part would be called recursion, because that's what we're going to be talking about for the next third of the course. Okay, the last part I'd probably call black magic hackery, because it's all about basically doing some just hacking BS to get some really interesting results. And by hacking, I don't mean like technical stuff. I mean like, oh, if we do this, well, this is a problem, so I'm going to create a hack to this. I'm going to hack up a solution right here, which has its own problems, but it's a smaller problem. And then I can work on that, and then I can create a weird hacky solution to that one, which has its own problem, but I can solve that one. And that's basically how we create hash tables, by just basically taking a massive problem and turning it into slightly smaller problems. But in order to learn how to take stuff and turn them into slightly smaller problems, that's the entire idea of recursion. Recursion is the point where basically I need to tell you that we need to learn how to be lazy, which is that we need to start thinking lazily. And a lot of recursive methods, as you'll see, like for solving the Tower of Hanoi, they're going to be like stuff that doesn't look like it should work. The code seems way too simple. It seems way too concise. I mean, it seems way too much like pseudocode, but it works because it's recursion. So we're going to learn how to think recursively. We're going to learn how to trace a recursive method, which means we're going to be able to go through one recursive call and see how that works. And we're going to start with some really basic recursive methods, like completely nonsense stuff. Basically, we're going to start with stuff that's just made up for the purpose of problem solving. Okay, maybe we're going to maybe do 1 or 2 real recursive methods in there when we just start. Then we're going to start looking at like actual recursive methods. We're going to learn how to write them, and writing recursive methods are actually very easy because they all are the 2 same steps, which are base case, recursive case. Once you solve those, the entire thing is done. We're going to learn also how to, I don't know why this is a separate point. We're going to learn about how to search arrays. We're going to learn basically the search method. And we're going to learn basically about one more big O notation, which is O of log n, which actually I don't know why people never explain how logarithms work, but that's probably because they always do logarithm base 10. When you talk about log base 2 is actually insanely easy to understand how that operator works. And and the explanation, believe it or not, is not going to have anything to do with exponents. So to learn about recursive data structures and recursive methods or a linked list, understand how we solve the Tower of Hanoi problem. They're going to do 2-dimensional images. How to apply backtracking to solve search problems such as finding a path through a maze. This is traditionally where I put in maze solving and stuff, but you can do it with stacks. Now, rather than doing 2D images, I like chess problems, like some classic chess problems, and I think it's really going to depend on what your homework is going to be, like, because I'm thinking ahead here, whether I'm going to give you whether I'm going to write a Sudoku solver in class or I'm going to leave it up to you, which is not actually too hard. Other classic recursion problems, I think, are like solving 2x2 Rubik's Cubes. So like the algorithm for doing Rubik's Cubes, I believe, are recursive. But the point is that it is solving things recursively is the elegant way to do things. It is where basically it becomes not so much an art, but a matter of like, of just basically the code looks clean. It looks concise. And it allows you to solve, it's another just problem solving thing in your tool belt. Sometimes it's easier to think about how to solve something recursively than it is how to solve linearly. We'll see that in trees. It's very hard to solve tree problems linearly. Instead, it's easier if you think recursively. So recursion is also big in AI. A lot of times we need it to write stuff like how to play a game of chess, which is way beyond what we're going to do here. Prove math theorems, how to recognize patterns, that's a big one. let's see. Recursive algorithms can compute factorials, compute the GCD, process some data structures, do efficient search. We're going to also learn how we can use recursion for a process called divide and conquer, where we divide up a problem and conquer the smaller problems. And the way we conquer the smaller problems is dividing them up into smaller problems and conquering those problems, and so on and so forth. And the idea here is that we are actually going to use that Russian nesting doll that we were talking about a couple weeks. And this is where it really is a Russian nesting doll. The idea here is that inside every Russian nesting doll is a smaller, simpler Russian nesting doll, right? And the idea behind recursion is that inside every recursive problem is a smaller, simpler version of that same problem. Now that doesn't necessarily make sense, but the idea here is that let's look at the classic recursive problem, and maybe we'll start to see how that makes sense. The classic recursive problem is the factorial function, okay? Which that was nice and undramatic there. Okay, so the factorial function, right? 5 factorial, right? Anybody need a review of what factorial is? Just in case, that does mean 5 factorial does mean 5 times 4 times 3 times 2 times 1. It grows really quickly. So this is, I think, off the top of my head, because I've done this example like a bajillion times, 120. Only reason, right? The math right there. So 2 times, so that's 6, right? 6 times 4 is 24. 24 times 5 is 120. So yeah. So I had it memorized. I didn't really, calculate in my head that quickly. So 5 factorial. So let's talk about like how we might do this, how we might write this in Java, right? The idea here is that I might have a function factorial, which I'll just call fact. Factorial. How do I write it out? Factorial int n. It takes in some integer n, right? It's public static nonsense over there, right? Okay. And the idea here is that the way we might do this is that we might have a int product. So we're going to do a running product as opposed to a running sum, right? Remember, running sums, we just add to a sum, right? And then we return the sum. Here we're doing a running product, so I'm starting with 1 because when we're multiplying by stuff, we don't want to multiply by 0 because then nothing's going to happen. Okay, so return product. Okay, and here's how to solve this problem non-recursively. So for int I is equal to 1, I is less than or equal to n. So all the numbers 1 through n, I plus plus. We are going to do product times equals I, right? So this is good. So if I passed in 5 over here, it would do 1 times, it would multiply this product by 1, then multiply by 2, then multiply by 3, then multiply by 4, then multiply by 5. Not the most elegant code in the world, right? It's just a for loop, right? But there's a couple things with it. First, it doesn't really fully express the mathematical meaning of it, right? It's just a for loop. Don't necessarily understand how it works just by looking at it, right? I mean, at this point you should, but you might not. And it's a mathematical expression. I mean, and there's nothing wrong with doing it this way. But doing it this way is what we call it doing it iteratively, right? Because we're using an iterative statement over here to solve it. A loop, in other words, to solve it. So we iterate through a loop and do this. The other way to do this is called recursion. The idea here is that we can realize we can get a better understanding of the problem. Now, I'm making recursion, by the way, sound like this awesome thing, which it is, but it's a tool. It's just a tool, okay? Just in the same way that the object-oriented programming is just a tool, right? If you think too long in one manner in that way, then you might have trouble thinking in some other ways. Like it took me forever to go from object-oriented programming to think about like stuff like, oh, we're in Python now. I can pass functions as a variable, right? Because I can totally say like I can define a function like something else and then set it to a variable and actually use it. Python allows a function to be be set as a variable because why not? Or thinking about stuff like a functional programming language, where like Lisp, right? So it's just a tool, and the tool indicates certain ways of thinking. So it's easy so recognize it for what it is. It's a tool. And the idea here is that if you have multiple tools, then you have multiple ways of thinking, right? The old adage that if you have a hammer, everything looks like a nail. Well, basically, recursion is just one more tool in your toolbox that you can look at a problem and see, can I solve it with this problem? How does that solve? Is this the right tool for it? In fact, I've read, and this might be apocryphal, this might be a liar, so if somebody on the internet is watching this video on YouTube and I am a liar, please comment, because the best way to be correct about something is to be wrong. The basically like programs like NASA for some of their rovers and stuff, they ban like using recursion in certain areas simply because it can be a bit dangerous in terms of coding when you don't know how far down you're going to go in terms of recursion. This is apocryphal. I read it somewhere on the internet, and as Abraham Lincoln wrote, don't believe everything you wrote on the internet, and I saw that attributed to him. So we can trust Abe. So, but the idea here is that it's a tool. You may not be able to use it, but it's a useful tool. So let's talk about how it works. 5 factorial, right? The idea behind 5 factorial is that it's 5 times 4 times 3 times 2 times 1. But here's the cool thing about it, right? If we actually look at this, right, summing up 5 factorial right over here, when you try to do this, if I asked you to do it, you could, but you're gonna be annoyed and go like, this is a lot of work, right? So, but if we're a bit clever and lazy at the same time, we might look at this and go, wait a second, this thing over here, 4 times 3 times 2 times 1, what is that? What is it in terms of factorial?
4 factorial.
It is 4 factorial. This expression over here is 4 factorial, right? So we came to this realization that 5 factorial is really just 5 times a smaller factorial, right? 4 factorial. Okay? And 4 factorial, it's really just 4 times a smaller factorial. It's 4 times 3 factorial, right? And 3 factorial is just 3 times 2 factorial. And 2 factorial is just 2 times 1 factorial. And 1 factorial is 1, right? The idea here is that basically that each of these factorials, right? That is a harder problem. Basically, it's not a lot of multiplication. It's one multiplication operation if you think about it. It's just 5 times 4 factorial. And 4 factorial is not that hard to figure out. I don't know what it is, but I can solve what 3 factorial is and then multiply that by 4, right? Well, to figure out what 3 factorial is, I need to figure out what 2 factorial is. All right, let's go ahead and actually graph that out just for a second. So the way I can solve this is by saying, let me figure out what 5 factorial is. Okay, and that is 5 times 4 factorial, and 4 factorial is, well, that's 4 times 3 factorial, and 3 factorial is 3 times 2 factorial, and 2 factorial is 2 times 1 factorial, and 1 factorial, well, actually, I need a place to stop at some point, right? So the first key for what we call a for solving problems with recursion is what we call the base case. Okay, and believe it or not, the base case is often the hardest part to write when we get into more complicated problems. The recursion is the easy part because recursion is just being lazy. The base case is sometimes the harder part, but in this case, the base case is simple. Basically, the base case is the thing that's so easy to solve that basically it doesn't require dividing it down into a problem anymore. Okay? So the idea here is that basically we need to come up with a base case, something that's a version of factorial that's so easy to solve that a subproblem of factorial that's so easy to solve we don't really have to think about it. So one thing for that might be 1 factorial, right? 1 factorial, that's just 1, right? That's one base case. And you can have multiple base cases as well. For instance, anybody know what 0 factorial is?
1.
It's 1, actually. I don't know why in the world it's 1, but it's 1. It's 1. So 0 factorial and 1 factorial, that's our base case. If it's 0 factorial or 1 factorial, we'll say it's 1. And otherwise, what we'll do, so basically, if we get to 0 factorial, 1 factorial, we'll return 1. Otherwise, what we'll do is that we'll do 2 times whatever the smaller factorial problem is. So here we got to 1. 1 over here. So now we can say 2 factorial is 2 times 1. So that's 2. 3 factorial would be 3 times 2. So we return 6 for 3 factorial. And then for 4 factorial, we're going to return 4 times 6, which is 24. And so for 5 factorial, we can return 5 times 24. Okay. We can actually put this down as a math equation, which is really nice. And then you'll start seeing why this is really cool. Okay, so we can specify that n factorial is equal to one of a couple of options, right? We can say that it's 1 when n equals 0 or n equals 1, right? Okay. Other option is that otherwise n factorial is equal to n times n minus 1 factorial, right? When n is greater than 1, right? What are we going to do for negative factorials, by the way? No idea. There are no negative factorials? You sure?
We want it.
Maybe. I mean, according to this definition, right? They certainly would. We'll figure that out in a second. Right now, we'll ignore the fact that negative numbers exist, right? So, so for right now, n factorial is equal to either 1 if n is 0 or 1. Otherwise, it's n times n minus 1 factorial, right? So 6 factorial would be 6 times 5 factorial. Well, what is 5 factorial? It's 5 times 4 factorial. 4 is 4 times 3 factorial. 3 is 3. So this is what we call a recursive definition for the factorial function. So let's go ahead and code it. And what you're going to see, and this is what's really cool about recursion when it comes to mathematical functions, is that it's super easy to just take a recursive function and change it into math. So let's go ahead and create a new class. It's going to be in, browse. It will be in classroom, code, in package recursion, evening, and we're going to call it recursion examples for my class. Create that. Okay, so let's go ahead and write our factorial function. Public static void factorial int n, right? Right? So rather than doing n factorial, I'm just calling this factorial n, like that, right? Make sense? Okay. So let's go ahead and go through this. So the first thing is the base case. The factorial problem that's so easy that basically that we don't really need to do any thinking about it, right? We don't need to do any computation, which is that if n is equal to 0 or n is equal to 1, right? What do we do? Return 1. Well, assuming you could spell it. Return 1. And they paid me because I have a computer science They're paying me because I have a computer science PhD, not because I have an English PhD. So, just keep that in mind. Okay? All right. So maybe I should probably call this. I'm also going to return a long here because this gets big really, really quickly. Otherwise, what should I do? Else, we do the recursive. So you have the base case, and then you have what's called the recursive case. The recursive case is this case up here where basically we take this problem, solve a little bit of it, and then say, I'm lazy, solve this easier version of the problem, which is that I return n times factorial of n minus 1. So look at that. The function is calling itself. That is the by the way, the key distinguishing feature of the recursion, and that is that the method calls itself, but it does so in a specific manner, right? First off, it's got to do so and make sure it's end. When it does so, it makes sure that this is going to end at some point. So, for instance, this over here that I'm writing, not recursion, out.println, this is not recursion. This function over here, not recursion, is not recursion, even though it's calling itself. Why is it not recursion? It's never going to end, right? This will, well, not true. It actually will end. I mean, in theory, it would never end. In practicality, it's going to end at some point, and not just because of hardware failure. So, not recursion. Boom. So print it out a whole bunch of times, not recursion. And then I got an error at some point saying that exception in thread main java.lang stack overflow error. Well, there's a term you might have heard before, just on a website though. Stack overflow, which we're going to learn about what that term is, by the way. But you now know what a stack is, right? You now know what a stack is, right? And the idea of a stack overflowing, well, maybe that means that we had a stack somewhere and we just put too much into it, which is exactly what happened here. We have a stack that your computer uses for doing computation, and when you do a method call, that's how it remembers where it is, and you just put way too many method calls in there for it to keep track of, and so it overflowed. Okay, we'll go into more detail about that in a bit, but that is not recursion, right? Recursion has to end. Every recursive call, the key feature of this is that every recursive call, in other words, every time we call factorial calls factorial, it has to make progress towards the base case, right? So you can see that, ignoring the fact that negative numbers exist for right now, right? That if we put in an n here, right? If we put in like 2 million, the next factorial call will be 199,900,000, and the rest of the digits, right? And then it's going to be one less than that. And it's going to be 7, and then 6, then 5, then 4, and then eventually it's going to get to the base case, right? So it's going to make progress. It's not an infinite loop. So let's test it to make sure that it works. So first things first, system.out.println factorial 5. Okay. Oops. So 120. Okay. Now factorial of 1 will return 1. Factorial of 0 will return 1, because if we told it if n is 0, 1, return that. If we pass in 5, it returns 120 because it does exactly what I graphed out there, which is that it figures out what 4 factorial goes, okay, it's going to be 5 times whatever 4 factorial is. 4 factorial is going to be 4 times whatever 3 factorial is. 3 factorial is going to be 3 times whatever 2 factorial is. 2 factorial is going to be 2 times whatever 1 factorial is. 1 factorial is 1, so factorial 2 returns 2. Factorial 3 returns 6. Factorial 4 returns 24. And factorial 5 returns 5 times 24. Which I know that was a bit much to follow, but that's the way recursion works. Okay. So every problem was a smaller, simpler version of itself. Every single call. Now, going to that, right? Now let's stop ignoring negative numbers for a second, right? What's going to happen if I put -5 down here instead? Well, what's going to happen? It's going to go on forever, or stack overflow, right? In theory, it's going to go on forever, but in practice, we're going to get that stack overflow error. And the reason is that -5, well, that's not 0 or 1, so n times -5 minus 1, that's -6, then -7, -8, so it's going to be going away from our base case. So negative numbers are no bueno. So let's go ahead and look up a negative factorial. Is that a thing? So it doesn't seem like it's really Is it let's see, factorial -4? Not really, it says. So we've got two ways to do this. We can give them an error, or we can just give them the negative of a positive factorial instead. Okay, so let's go ahead and say else if, and let's do some incorrect math here and say if n is negative, right? If n is less than 0, we're going to go ahead and give them this instead. Return -1 times factorial of -1 times n. What's going on there? Well, n is a negative number. Multiplying it -1 is going to turn it positive. Okay, so if I pass it -5 now, it's going to compute, it's going to compute the factorial of +5, and then give me the negative, and then throw a negative side in front of -120. So now if I run this and do -5 factorial over here, it gives me -120, which probably isn't correct math, but whatever. It's a solution, even if it is not the mathematically correct one. Okay, and it prevents us from getting into that infinite loop or Stack Overflow. Okay. Now, here, the idea here is that will this ever go on forever, putting in a negative number? No, because the negative number calls a positive number, but a positive number will never call a negative number, right? And once you're into positive numbers, you're going to start going down to the base cases, right? So, so let's go ahead and see basically what we know for our conditions for writing recursive methods are so far. So what we've got for writing recursive methods are 3 rules so far. You need, first off, you need a base case. Which is basically our super simple, no thinking solution. Right? Not always true, as we're going to see, but it's for right now true. Our recursive case solve part of problem and call function on smaller part. So this is basically the recursive case over here in our code was, so our base cases over here was this, where we just returned 1. And then here, we solved part of that problem, right? Here, if we passed in 5 factorial, we solved 5 times. And then we did, we said to do factorial of n-1, which is solve the rest of it, solve the smaller problem, right? The idea here is that the recursive case always gets smaller. And rule 3, recursive case always makes progress towards the base case. Okay? Those are basically the 3 rules. We'll see if there's any more later, but these are pretty much the 3 rules that I think of when it comes to recursion. You've got your base case, super simple solution. You've got your recursive case, which is that we solve part of the problem. And then we say that the recursive case always makes progress towards the base case. So let's see what the slides have for us to say about these. So let's see. I'm going to go and skip here and think about. Let's think about like some super easy problems, like problems that we don't normally need to think about recursively. And then we'll possibly get into an actual problem tonight. Okay, so recursive algorithm for finding how long a string is, right? So here we got to come up with a base case and a recursive case. The base case is if the string is an empty string, if it doesn't have any characters, then the length of the string is 0, right? Otherwise, the recursive definition for this is that the length of the string is 1 plus the length of the string of the rest of the string. It's 1 for the first character, and then the length of all the other characters but the first character. So this is a really stupid algorithm again, but it's useful for showing. Here's a base case, right? Passing the string. If the string is null or it's the empty string, then it's 0 length. Otherwise, the length of the string is 1 plus all the rest of the string. Right? Now, we could totally just do... Now, this is one of the cases, definitely one of the cases where recursion is not the optimal solution, right? The optimal solution is to call .length, which is a constant time operation. If the length of the string is n, then what is the big O time for this algorithm? O to the n. So this is a linear time solution for finding the length of the string, which is impressive in some ways that you managed to make it so slow. Let's go ahead and look at this one. Now this is actually kind of cool here, what they've got going on over here. And I'm actually going to copy it out because it shows that basically that sometimes when you make something recursive, you get a bit of versatility from it, even if it's going to take longer. Control A, Control I for Eclipse to auto indent. So here, public static void print characters, which is going to print all print all the characters of the string 1 line at a time. Which even if you did that iteratively, it would still be O of n time because you're printing one line at a time. So same thing, base case. If we have a if the string is null or if it's empty string, we're not going to print anything out. Notice that we have a return and a void, but notice that the return doesn't actually, stop anything. If you remember, what happens when you hit a return statement with any function is that you just stop wherever you are. So here, like in a void method, hitting a return is like hitting a break for the entire function, like how break stops a while loop or a for loop. Here, the return just acts as a break, which is kind of clever, right? I mean, mind you, in this function, we could just get away with this, Also, notice that basically they didn't have any curly braces. When you just have 1 line of code, you don't need curly braces. However, this is considered bad practice because if I decide I do need a second line of code, like this, system.out, print line, okay, if I need a second line of code, like over here, done. Now notice I get an error over here on the else, and this is because the else is no longer attached to the if. What would happen is that if there was some compiler error there, is that we'd go if, we'd do the if statement, it would only consider done to be part, this system.out.println done to be part of the if statement, and this return would be right over here. Meaning that basically that it would never hit the else. So as a result, I highly say, even if it's just a one-liner, put curly braces around it. Okay? If you really want to be space efficient and keep it at 1 line, you can totally do this. You can just do this, and that's even safer. Right? But anyway, that's neither. Okay, so otherwise, so here we've got our base case. If it's null or an empty string, we do nothing. Otherwise, we print out the first character, and then we print out the rest of the characters. That's the recursive thing. I solve a bit of it, and then I throw the problem at the rest of I do the rest of the recursion. So let's go ahead and do print cars CIS 2168 because I'm being unoriginal right now. Okay, so run it, and it will print out CIS space 2168 and then -120 because we still have that there. So we'll comment that out. But what's cool about this is that we can actually swap these 2 lines here, and something interesting will happen. So let's go ahead and take the print characters, cut it, and move it above the print line statement. So here, the recursive case is print out the rest of the characters, then print out my character. Now what happens? If the statement is it was print out my character, then print out the rest of the characters. Now it's print out the rest, then print out mine. What does that do? It prints it backwards. So 8612 SIC. Right? This, which sounds like a weed out course of some kind. So you know, 8612 SIC. So, so here, just by making a simple change, we were able to completely change the way it worked and come up with actually something that's pretty useful. So let's go ahead and keep going on this. How do you show that a recursive method that you wrote it correctly? Well, we can kind of use, so how many of you have taken math concepts enough to learn proof by induction? 1, 2, 3. Okay. Did anybody like, okay, so let me rephrase that. Has everybody heard the term proof by induction before? No? Okay. So some of you have, and for those of you who haven't, let's go ahead and explain. The way proof by induction works is that it's one of my favorite ways to prove something because it seems like magic and it seems really easy. You show that that some theorem, some equation is true for the base case. So we're going to go back to one of the cases that we were talking about much earlier, which is one of the classic proof by inductions, which is showing that this equation, 1 plus 2 plus 3 plus 4, all the way to plus n, is equal to n times n plus 1 over 2. So this is a classic proof by induction problem, okay? And the way it works is by saying it's a two-step problem. First, you show that this works for a base case. So in other words, we choose some base number, such as n is equal to 1, and show that it works. So 1 is equal to 1 times 1 plus 1 over 2. So this is equal to 2 over 2, which is 1, which is equal to 1. Right? So it works for a base case. Then what you do for induction is that you show that if we can assume that it's true for some n, then if we can show that it must be true for n plus 1. So in other words, what we do is that we'll swap out the numbers and say we're going to assume that basically that since it works for k, right, for some number k, and if you're having trouble thinking like in terms of k, well, since it's 1, we're going to show that if it's 1, it must be true for 2. If it's true for 2, it must be true for 3. But we're going to do that in terms of variables. So here, we're assuming that it's true for k, so we'll show that it's true for k plus 1. So k plus 1 is equal to k plus 1 times k plus 1 plus 1. And I'm not showing it on the camera, so might as well. So k plus 1 over 2, right? And that seems like a really hard equation to solve or something. And there's some distribution to do there, which I'm not going to do. But the trick is that basically we go, wait a second. We're assuming that this equation holds true for 1 through k. So I can replace this with k times k plus 1 over 2. And now I just have to show that these two sides are the same to show that this equation holds. So to show that this theorem works. And that's how proof by induction works. Basically, you show if it's true for 1, and then if you show that it's true for the general case, and then you can show that if you can show that it's true for the base case, and then show that the more general case works, then you're in business. And the idea here just involves just distributing these numbers around. In other words, we multiply these things out and then just show that basically the two sides distribute out to the same way, right? It's just setting those two sides equal to each other, which is something that has basically been on every single proof by induction concept, so proof by induction exam since like the beginning of time. So showing that your recursive function is that is going to work is very similar to that proof by induction, but in my personal opinion, it's easier. You show that the base case is actually the base case, right? The base case actually it works, right? So in other words, create a base case. Step 2, verify that the recursive case makes progress towards the base case. And step 3, show that basically if you do all the recursion, then if you basically, since recursion breaks it up into little parts, show that if you solve all the little parts and put them together, it's going to give you the big part, right? In other words, this is saying, well, 5 times 4 factorial uses 3 factorial, and we use 3 factorial to do 4 factorial, and 4 factorial to do 5 factorial. Show that if you put those all together, it's going to work. And this is called, and you do that by tracing the recursion, or you can do that part of it by retracing or unwinding the recursion, which is what I was doing on the board over here. So the length, for instance, the length of ACE, if we're solving that recursively using that recursive function earlier, it's 1 plus the length of CE, which is 1 plus the length of E, which is 1 plus the length of nothing, which is 0. So that returns 1 plus 0, which returns 1. So we've got 1 plus 1, which returns 2 as the length of CE, which returns 1 plus 2, which is 3 as the length of 3. So this is the idea of unwinding your recursion. Basically, you can just trace it down and then trace it back up. All right. So now let's go into detail about that stack in the stack overflow error, which is that we have something called the runtime stack. And yes, it actually is a stack. And it saves basically any new information that you use in the form of an activation frame. So an activation frame is what actually gets stored on the stack, this stack that your computer uses. So in reality, when you're doing stuff with recursion, you're really just using the stack. So anytime that you need to solve something recursively but can't do recursion, you can use a stack instead. So the activation frame basically stores the method arguments, any local variables you create, and the return address of the instruction that called the method. In other words, where to go. This is how your computer knows to go back to a specific place during the method call, right? When you go from a method call, you go into a function. Well, how do you get back out of the function? Well, your method, the activation frame, is storing the address of where you should come out. So whenever you call a method, whether it's recursive or not, you push that activation frame onto the runtime stack. So here, for a length of, here's an example. When we did length of ACE, well, that did 1 plus length of CE, which was this frame, and then that would call length of E, which would call length of empty string, right? And then it would solve the length of empty string and pop the result, and then pop that and return the result to this frame, right? If that's a bit much, don't worry. We're getting into like system level programming stuff here, which is not the point of it. But the point is that basically that recursion uses a stack. The analogy they like to use, which I also like, is that you've got an office tower, and an employee at each level has the same list of instructions to do. The employee at the bottom level, what they do is that as part of the instructions, they call the employee the next level up, and they get put on hold. Then the employee on the next level completes his part of the instructions, and then calls the employee on the next level to give him his part of the instructions. And the guy on level 2 goes, okay, give me a sec. I'm going to put you on level 1 on hold. And then he calls the guy, he does his part, calls the guy on level 3, says, here's your instructions. And the guy on level 3 goes, okay, hold on, I'm working on it. I'm going to put you on a brief hold. Then he calls level 4, and so on and so forth, until you get to the top level. Is this making sense so far? Basically, they're all solving a small bit of the problem, and they're just calling up to the top. Then the employee on the top, he gets his call, he goes, oh, that's an easy problem. I don't know why you guys are calling me to solve this. So he returns so at level n-1, he's put on a really brief hold. The guy below him is on a slightly less brief hold because he gets the answer. And then we finally get all the way back to the bottom. The poor guy who's been on hold forever, right, is kind of the idea. They all complete their problems and pass the answer back to the employee below. Eventually, you get to the bottom and everything's put back together. So that's not something I'm really going to test you on, but that's just the way it works, and that's why you get sometimes these stack overflow errors. So for instance, with this factorial function, let's just go back over here. Factorial is actually first off, factorials grow really quickly. Factorial of 20, by the way, is this giant number over here, which is bigger than an integer. So the problem is actually that basically not that factorial is going to get too big. Well, let's see how big this not recursion function gets. And I'm going to actually kind of make this recursive, only not really recursive because it's not going to end. what I'm going to do is that I'm going to have this. I'm just going to create a static counter equals 0. So static int counter, okay? Counter plus plus, right? Here we go. So basically, I increment the counter, and now we'll be able to see how many times this has been called, right? Because we've got this static int over here. So, oh, yeah, got to make sure it actually runs something first. So let's run not recursion. Okay, so it ran for a bit, and then it gave us an error. See? Oh, wow. That's interesting. Okay, so let's go ahead and, since this is throwing an exception, right? This is throwing a stack overflow exception. Let's do a try this. And this might be a bit foolish of me. I'm going to try calling not recursion. And if that gives me an error, catch system.out.println. So I'm going to catch any exception that gets called. Instead, if I can't do that, then I'm going to print out counter. Make sense? See if this actually does anything. Oh. Stack overflow error. It doesn't really give me the chance to figure it out, does it? Try it again. Nope. And it's probably, let's see. Counter plus plus. Oh, I thought I saw something for a second. But no. Alas, no. Let's go ahead and... So yeah, I really can't tell how far this goes. I forget how far I was able to tell how far it would go before it crashed. But I've been able to get to like 10,000 deep on these things, like 10,000 method calls before this crashes. So I forgot how I did it last semester. Okay, so let's go look at some more recursive problems. So mathematical formulas are great for recursive problems, but not necessarily all of them. So first we're going to look at some good mathematical problems, which we've already looked at, factorial. Then we're going to look at Fibonacci, which should almost never be computed as the math function, as written by like in a math function. So we've gone over factorial, right? So what we're going to look at is now the x to the nth power. So if we're raising something to the nth power. So right now I'm going to replace x with, like, again, 2. Right? And the idea is, how can I calculate 2 to the n? Right? So again, what I'm going to look at is I'm going to give our same idea of 2 to the 5, and I'm choosing 5 because that's a pretty nice, easy way to do recursion. 2 to the 5, it's just big enough to make a recursive case about it. 2 to the 5 is really 2 times 2 times 2 times 2 times 2. 2 multiplied to get there 5 times, right? So a recursive, if we're thinking about it recursively, we could go, well, 2 to the 5th power, that's just 2 times 2 to the 4th power, right? So 2 to the 5th power is just 2 to the 5th power times, it's 2 to the 5th is equal to 2 times 2 to the 4th, not 24, 2 to the 4th power times, which is 2 times 2 to the 3rd power, which is 2 times 2 squared, and that is 2 times 2 to the 1st power, and that is 2 times 2 to the 0th power, which will be our base case, right? Because what is 2 to the 0th power? It's 1. Anything to the 0th power is 1. That's going to be our base case. Okay? So let's go ahead and write this. So our base case for for let's go with the POW function. POW, so public static void, double POW is going to take in a double base and a int exponent, because we're just dealing with, raised to the nth, so some integer power, as opposed to the complicated raised to like a fraction. Okay. So our base case is we are going to return if exponent is equal to 0, return 1, right? Anything raised to the 0th power should give us 1. Else, we want to return the recursive case, which is 2, which would be base times, so it would be x times the same number raised to the n minus 1 power, right? So base times, so here we've got, basically it would be, in this case, if we passed in 2 and 5, it would be 2 times 2 raised to the 4th power, right? Then it would be 2 raised. Does this make sense to everybody? So now, let's go ahead and try calling it. So now, print line POW 2 to the 5th power, 32, right? 10 to the 5th power, 100,000. Cool. Again, we're dealing with the problem of what if we raise something to the negative power, though, right? If we raise something to the negative, if we pass a negative exponent into this, right, we're going to get in an infinite loop, right? Because it's just going to keep calling that. So instead, what we need is, we'll put an else if over here. Else if exponent is less than 0, we need a way to handle that. So what should we do? Well, if you recall, it's actually not too much of a problem, because if you remember, 2 to the negative, so actually, let's go with 10, because that's a bit easier for you to compute. 10 to the negative 3rd power is just equal to 1 over 10 to the 3rd, right? It's 1 over 1,000, right? So all we have to do is return 1.0 over POW base negative negative 1 times exp, right? So now flip the exponent sign and return. And again, we're never going to get into an infinite loop with a negative exponent over there. So let's verify it, and let's go ahead and verify it. 10 to the negative 3rd. Okay, that's pretty cool. Let's look at a kind of a different algorithm, though, one that is made for recursion, but one that you may not know yet, or maybe you've been experienced to it. If you've experienced it yet in a math concept class, the GCD algorithm. So the greatest common denominator of two numbers, or greatest common divisor, right? You probably heard it called both things. Is the largest number that divides both. So for here we've got 20 and 15. The biggest number that divides both of them is 5, right? Biggest integer. 36 and 24, it's going to be 12, right? 38 and 18, biggest number that divides them both is 2, right? They share no other common divisors. And 17 and 97 are both prime numbers, so they don't share any common divisors except for 1, which is 1. So the recursive algorithm for this, there is actually an algorithm to solve this, rather than, because if you've been like me, if you were like me, you probably like brute force these things whenever you were going through math. So the recursive algorithm for doing these, though, involves using modular. And so now we can actually have an algorithm for solving these things. So first, we are given two positive integers, m and n. I'll call them big and small because m and m sound way too much like each other, which is why I've always hated them, using m and m as variables. So I'm going to call them big and small. So if small is a divisor of big, in other words, if small divides big, then the GCD is the small number. Okay? Otherwise, the GCD of the big and small number is equal to the GCD of the small number as the first argument, and the big number mod the small number as the second argument. Wait, what? Right? So let's go through that. Okay, so let's go ahead and do that. So we're always going to assume that the big number is going to be given over here. So let's see, 20 and 15 is 5. So big, small, let's call it big mod small. Okay, so I'm just going to make a table to show you. Okay. So here, let's start with 20 and figuring out what the common denominator of 20 and 15 is. And if I'm accidentally given 15 as the as the big number and 20 as the small number, it's pretty easy to check if those two things, if one is bigger than the other, and just swap them. Okay. So does this number divide this number? Sorry, does this number divide this number? No, it does not. Not evenly, right? So instead, I'm going to calculate big mod small, which is going to be 20 mod 15. That's going to give you a remainder of 5. Okay, and now I do the same algorithm, but I use 15 as my big, and this number 5 as my small. Okay, and now I compute big mod small. Well, first, actually, I asked, does this one divide this one evenly? Yes, it does. So I'm done. Okay. Okay. Give me two numbers, both of which do share. Actually, just give me two numbers.
7, 23.
7 and 23. Okay. So 7 and 23. So small is bigger than big. Sorry, small is bigger than big, so I'm going to swap them. Right? So 23. Does 7 divide 23? No, it does not. So what is 23 mod 7? 2. So now for the next iteration of the algorithm. Does 7 divide 2? No, it does not. So let's calculate 7 mod 2.
1.
Does 1 divide 2? Yeah, it does. 1 divides everything. Right, kind of a trick question there. So 1 divides 2. 1 divides 2, so we're done. We return 1. Okay? Okay, let's go ahead, and I think it was 38 and 24 was another one. 38 and 24. Big mod small is, so let's see, I think that's what, 14? Right? So divide this, that goes in once, so let's just subtract 38 from 24. Sorry, 24 from 38, we get 14, right? So 14, so now we use 24 and 14. This does not cleanly divide this, so we do this minus this, which gives us 10. That's just the easy way for us to figure out if it divides by 1, if it's evenly divisible, so if it divides into it once. So now we've got 14 and 10, so these don't cleanly divide. 14 mod 10 gives us 4, 10, 4. So this gives us a remainder of 2. 4 and 2. 2 is actually divided by 4, so we return 2. So this is a recursive algorithm, even though it's a bit different than the other ones we've been doing. Okay? It's recursive because we're doing the same process over and over. Okay, so our base case, so let's see what our base case is. Base case is that big is divisible by small. Okay, that's a base case. If so, return small. Otherwise, our recursive case was we call the same function with the argument small and big mod small. And so the question is, does each of these, so now we have to verify, does this problem make progress towards the base case? Well, we get smaller and smaller numbers, and the divisor is always going to be equal to or smaller than big. So, so these numbers become smaller. They eventually work themselves all the way down to the 1. 1 is the last possible thing we can check, right? Because everything is divisible by 1. So these progressively get smaller and smaller, and if small doesn't divide big, it's eventually going to get to 1. So this will make progress, and it will end. So let's go ahead. So in other words, since we get to 1, we'll always hit the base case. So public static int GCD int big int small, right? Rather than M and M or int M and N. This is exactly my point. It's also why I hate P and Q. In computer science, you can use more than a couple letters for a variable, so you might as well. Okay, so first off, if small is greater than big, right, which is, we'll just return the GCD of big, small. We'll just swap them, right? That only can happen once, right? So it's else if big mod small equals 0. So that's our base case right over here. If big mod small is equal to 0, if big is divisible by small, return small. Okay. Else, our recursive case. And technically this is a recursive case too, but it made sense to put it first. Yeah.
Are you supposed to return small big instead of big small where small is greater than big?
Oh, yes, small big. Thank you. Because that would just be the same argument over and over again. Let's see. The other thing we could do here is just simply say we could just simply do the 3-line swaps at small temp equals small, small is equal to big is equal to temp, right? Otherwise, over here, GCD, a really good catch there. GCD small, big, mod small. And that should be it. So assuming I didn't make another silly mistake somewhere, so let's go ahead and try the GCD. Give us common denominator of 155, which should be 5, right? Of 917 and 22, which probably shouldn't share anything. 1. So it works out fairly well. It's a fairly efficient algorithm for doing so. How efficient is recursion versus iteration? Because, right, and again, iteration is doing it by a loop. So here in iteration, a loop repetition condition, it checks to basically see, each condition it checks at the top whether or not this condition is true and whether or not we're going to continue. Over here, we're going to check in recursion whether or not it's a base case. And you can always write an iterative solution for a recursive problem. So the big thing is that recursive algorithms are often, once you know how to do stuff recursively, it's often easier to write a recursive algorithm. This is pretty big because on my exam, like on my second exam, when you do have to write a recursive function that goes over trees, I give you the entire page to come up with a solution for like one of the problems. Most of the time they can be solved in 1 to 4 lines if you know how to do recursion. And that includes the if statement and the else statement. So these recursive functions are actually make things ridiculously easy if you know what you're doing. And they're easy to write, code, and read, and that means a lot. But oftentimes it's slower to do recursion. Okay, sometimes it's slower because method calls takes a more amount of time to do a method call than doing a loop. However, that doesn't mean you shouldn't use recursion. You probably should because again, they're easy to read, easy to write, easier to debug. Yes.
In which case would it be slower?
It would be slower if recursion slower most of the time.
Just slower in general?
So it's slower in general. But often, sometimes, if you do something recursively, it's easy to write something that has a faster big O notation. And a lot of times, the reduction in efficiency for doing recursion usually does not outweigh the advantage of readable code that is easy to debug. I haven't said this before, but code is read a heck of a lot more times than it's written. Case in point, the code I just wrote now. I wrote it once. We read it like 30 times between each of us, right? So, your code, or if I'm just one person, I'm going to be reading my code a heck of a lot more. So I want to make it as easy to read and easy to figure out as possible. Recursion is a great way to do that. And that accounts for a lot of in programming because when you're less likely to make mistakes, expensive things are less likely to break. So I'm going to my last problem for the night is going to be, one last thing, is going to be a case in point of when not to use recursion. One more, sorry. But once we get here, it's like the perfect stopping point. And it's an excellent example of when not to use recursion. How many of you know what the Fibonacci sequence is? Yep. Thank you, Dan Brown. And for those of you who don't get the reference, that's the Da Vinci Code. So I'm just going to call it fib. And this will count the nth Fibonacci number. So let me first define what the Fibonacci number is, and we use the Fibonacci sequence for that, which starts off, and it's a great example of recursion. It's actually fantastic. It was the first recursive thing I ever learned, which was it looks like this: 1, 1, 2, 3, 5, 8. What's the next number? 13. What's the next number? 21. What's the next number? 34. Okay, for those of you who haven't included in yet, it's just simply the next number in the sequence is the previous two numbers added together. In other words, the recursive definition looks like this. Fib of n is equal to, so it's equal to 1 if n is equal to 1 or n is equal to 2. So the first and second Fibonacci number is 1. Otherwise, it's the fib of n is equal to fib of n minus 1 plus fib of n minus 2. So now we're going to watch what happens here. Okay. And then we're going to watch what happens. It's going to work, and then I'm going to up the antes, and then we're going to see that, maybe we're having some trouble. And then when we get back, we'll see what happened, how we fix this. So if n is equal to 1 or n is equal to 2, actually let's go with if n is less than or equal to 2, return 1. Else, return fib of n minus 1 plus fib of n minus 2. Okay, so let's go ahead and run this. Fib of, so the fifth Fibonacci number, 1, 1, 2, 3, 5, would be 5. The 10th Fibonacci number is 55. The 20th Fibonacci number, let's see what that is. 6,000 or so. Wonder what the 40th is. That was a bit weird. There seemed to be a bit of a lag. Let's check out what the 50th Fibonacci number is. There's a bit of a lag. Now, what's gone on here is that I have unwittingly written an exponential time algorithm, which means that I've unwittingly run something where if my input is n, it takes 2 to the n time to calculate. Not linear time, not n squared, 2 to the n. It's still going. So it took 2 to the, in other words, from 40 to 50, it took 2 to the 10 more time to calculate it. So we're going to go into further, so when we get back, since you all seem antsy to get out of here, we will go into more detail as to what the heck's going on with this, why that is.
What if use a for loop?
So, what?
When you use a for loop, would it end linearly, or?
Yeah, it should be linear when I use a for loop. It just happens to be that the way I did my exponential time algorithm was, there are ways to do this recursively that do not, in fact, make it run forever. But, you know, sometimes it's just better to use a for loop, and we'll get into that. So next lecture, what's going to happen is that we are going to go over this. We'll go over the recursive data structures, which are, so when I say recursive data structures, I mean like we'll go over linked lists, but we'll do them recursively. On Thursday, you will get a review, you will get a practice exam, which will look, you know, it will look a lot like your actual exam. And that will, and I'll basically post an answer video. So I probably won't go over it in class. I won't go over the practice exam in class. So if you have questions about it, come see me during office hours or send me an email. But I will post a answer video online, basically where I'll go through the exam question by question, and so you can go through it at your own pace and try to solve it. I highly recommend taking the problems one at a time and basically treating the exam as practice exam as an actual exam to see how well you'll do on the actual exam. All right. With that, I'll see you in lab, and then I'll see you next week.